Well, this unit is called, or this section is called Quadratic Relations, and there are actually other quadratic relations besides quadratic functions. We can talk about polynomials up to the second degree, but we could have a square on both x and y, for example. And one of the things that we can look at is a circle that turns out to be this. So if we take something that looks like x squared plus y squared equals r squared, where r is a fixed number, like in this example r is 5, that gives us a circle centered at the origin of radius 5. So if you take this point right here on the circle, has coordinates x, y, this is absolute value of x, this is absolute value of y. Square those, you get x squared and y squared. They add up to be r squared by the Pythagorean theorem. So the equation of this circle is x squared plus y squared equals r squared. Now, of course, you can shift it around. We know about this. We've talked about shifting functions or relations. This is not a function, but a relation. And we can replace x by x minus h and y by y minus k. And so this is a general circle. So the general form for a circle is right here. The center is hk and the radius is r. Now what if we stretch it a little bit? If we stretch it in one direction by replacing, let's just start with the original one, x squared plus y squared equals r 1. Let's start with that one, the unit circle. If we stretch it in the x direction, we replace x by x divided by a, stretch or compress, and y by y divided by b. That gives us an ellipse. So let's take a look in Graphmatica here. So if I start with x squared plus y squared equals 1, this is a circle of radius 1. If I replace x by, say, x divided by 10, that's going to stretch that out 10 times as far from the y-axis, so horizontal stretch. Notice that vertically it didn't change any. Now let's take that and replace y by, say, y divided by 4. And that's going to stretch it in the other direction. So these shapes are ellipses. Okay. Of course, then I can take that and replace x by, say, x minus 5. That'll shift the whole thing to the right 5. And I could replace y by, say, y, how about y plus 8. And that'll shift the whole thing down. And so we can see that. So in general, we can get an ellipse here, and actually it turns out that within this form, x minus h squared over a squared plus y minus k squared over b squared equals 1. Whatever this point here will be hk. Let's see, I don't have one centered somewhere else, but this would be hk, and this the center, and this distance here, this horizontal radius is a, and this vertical radius is b. Okay, and of course if a and b are the same number, that's the radius, and you get a circle. So a circle is a special kind of ellipse. Now if you're going to put this in your calculator, you have to solve for y, and you can't do it in one single equation, but you could do it with 2 square roots, and one square root would be the top half and the other square root for the bottom half. Okay. Now, if you notice that is this form right here where you have plus in between, this is positive as well. If you change that to minus, everything the same, but that's a minus, or this one's a minus and this one's a plus, or that's a plus and that's a minus, you get a hyperbola. Let me show you how that works. Let's clear this out. Let's do one centered at the origin right now. Let's say x over 5 square, this is going to be an ellipse, plus y over 3 square equals 1. So that's a horizontal radius of 5, vertical radius of 3, centered at the origin. Now look what happens if I change this to a minus here. It touches there and goes out the side, so you get these two pieces. This is called a hyperbola. If we leave that one a plus and make the other one a minus, now it's a hyperbola going that way. The interesting thing about these is if I take this point here at 5, 3 and the origin, let's see if I can write an equation for that. We put a line that goes through there. That's going to be an asymptote. So 5, 3, that's a slope of 3/5. Y equals, 3/5. 3/5 x. That is an asymptote for either one of those two ellipses, the blue one or the green one. And let's see, the opposite of that is going to go the other way. That's an asymptote too. So hyperbolas have asymptotes. Okay, so we're not going to really do a whole lot with this, but I did want to at least show you what that looks like. And if you have systems of quadratic equations, systems of equations with these kinds of quadratic relations, like these two here, which, well, let's graph them. X squared over 25 plus y squared over 9 equals 1. X squared over 25 minus y squared over plus y squared over 9 equals 1. That is an ellipse. And if we take this other one, x squared over 16 minus y squared over 9 equals 1. This is a different hyperbola, and we see that we get 4 places of intersection. So we could graph these on our calculator. It's actually going to take 1, 2, 3, 4 equations to get all this graphed on the calculator, and then we could do a calc intersect. So that's one way to do it. Here are the 4 equations that you'd have to do. So here I multiplied by 9 and 25 to get this, and by 9 and 16 here to get this. So we have this is the same system of equations. It might be given that way. If I solve this, each one of these for y, I get these expressions here, and I get those 4 functions, which would be the ways to get that graphed in a calculator. And if I want to solve this, I can use some techniques that we did for solving equations before. I can use elimination, like let's see, I believe that was, these were already the same. We just got to multiply by -1 to get them to be opposites, and then this will cancel out, and now we can solve for y squared. And when we take the square root, you get plus or minus. So here it is as a reduced radical with a rationalized denominator, or there it is with the rationalized numerator. And we can take that, and for each of those y's, there are x's that go with it. So it turns out for each of those y's, there's 2 x's, so that actually gives you 4 values, and there they are exactly and approximately. And if we want to do it approximately on our calculator, we could do it there. So here's some systems of equations. This one here, for example, you want to take that and substitute in place of the y here, and then solve that equation, which is a quadratic. Here, you're going to, if it's one's linear, you're going to probably do it by substitution. So either solve for y or solve for x, and then substitute. Say solve this one for get this one to look like y equals something, and put that in place of the y there. In this case, when they're all x squares and y squares, elimination works nicely. So take this bottom one and multiply by 2, and then add them, and the y squares will cancel out. Here, just add these together, and these will cancel out. In fact, I can do this real fast. This is the easiest one of all. So x is plus or minus the square root of 8. Okay, so now we know the x's, and then you plug in the x's here. Either x is going to give you two different y's. Okay, and of course be sure you check it and make sure that it works in both expressions. Okay, a couple other miscellaneous things that we can do. Each of the situations here, there's exactly one quadratic function that goes through that satisfies those characteristics. See if we can figure out what the formula is. In fact, let's give all the three main forms. So if we know the vertex and a point, that's going to be enough. So we start with the vertex form there, plug in the vertex, and we're still missing a. So we've got our formula, there it is. We're just missing the a value. We don't know what the a value is. Anytime you have a formula and you're just missing one constant that you don't know what it is, you can take a point that you know and plug it in. So in this case, I plug in the 5 for x and 7 for y, and when you do that, you can solve for the a. And you can see that the details are pretty straightforward from there. Once I have the a, and once I have the equation there, now I've got the whole equation. Once I have that, I can just expand this out, distribute, combine like terms to get this version. Then I can find the roots either from this version here or from this one with the quadratic formula. And it turns out this case they're non-real roots. So that means when I graph these, it doesn't cross the x-axis. Another example of the same thing there. Alright, what if we're given the roots? If we're given two roots, we can use this form and plug in the roots, and again we're missing the a. Again, we just plug in a point we know here, and we can solve for a. Now we have that form. Multiply, out, distribute, we get this form here. Average these two roots, negative 3 and 5 average out to be 4, so it's x minus 4 squared. Same a, all three cases. And then plug in the 4 in either one of these first two formulas to get 1/3, so we know that's the formula there. Alright, this is an interesting one. If you've got 1 point, there's exactly one horizontal line or 0-degree polynomial that goes through it. If you have 2 points, there's exactly one linear function that goes through it, provided they're not the same point, of course, or on top of each other. And then there's still one line, but it's not a function. But if there are 3 points, it turns out there's exactly one quadratic function that goes through those 3 points. So how can we take those 3 points and find the quadratic function that actually goes through those? Well, here's our formula. Let's say we take that version of the formula. If I plug in 4, 5, we get a true statement. So if I plug in 4 for x and 5 for y, I get this statement, and if I reorganize it, it's 16a plus 4b plus c equals 5. Now plug in 3, negative 2. 3 for x, negative 2 for y. Solve that around, and it looks like that. Then plug in negative 4, 7, and we get this. So what do I have here? Now I've got a system of 3 equations, 3 unknowns, and they're all linear type equations. Back in our linear chapter, we knew how to do that. We can put that in our calculator here, do the rref command, and get this, or we can do the reduce, or we can do this by hand, the same thing. but we're solving a system of linear equations. We know how to do that. Once we do that, this is A, B, and C right there, and so there's your equation. We can find it that way. Okay? What about quadratic sequences? So, a constant sequence, all of these terms are the same. So they have a difference of 0. They're the same. If it's linear or arithmetic, they have a common difference. So that they are going up by the same amount. The differences are constant. Well, it's kind of interesting. Let's work out some things here. So let's put in n as 1 here. 1 squared is 1 plus 1 is 2. Put in 2. 2 squared is 4 plus 2 is 6. Put in 3. 3 squared is 9 plus 3 is 12. Put in 4. 4 squared is 16 plus 4 more is 20. Let's do one more. 5 squared plus 5 is 30. Now, if I do the differences, I get 4, 6, 8, 10. Do you see a pattern? If you do differences again, it's the same thing. Those are constant. So the second differences are constant when we had a quadratic, and that's not a coincidence. It's always true that if you have a quadratic, the second differences are constant. In fact, if you have a cubic, third differences are constant, and so forth. So it's a characteristic of polynomial functions. So if we do this, of course the term numbers are 1, 2, 3, 4, 5. Once we see that we have a second difference that's the same, we know it's quadratic. Now we could take any 3 points, like these 3 points, and find the equation just like we did in this example right here. So that's what I did here. Here I see in this case the differences are 0, 2, 4, 6, 8, 10. Second differences are 2. And we can work this out. And I pick the first 3 points here. Plug them in. Here, here, and here. Here I use 1, 0. Here I use 2, 0. And here I use 3, 2. I got this system of equations, which I can write as that matrix. Solve it. I get this here. And there's my equation right there. Of course, I can also factor it or write it in vertex form. Okay. Alright, let's just finish up some things here. Remember, we can do regression. Bringing back things that we've done for other things. We talked about linear regression, power function regression, logarithmic regression, exponential regression. We can do quadratic regression as well. So here we put our data in. Remember how we do regression? This is some actual data from the Fort Smith Public Schools for 1984 to 1994. The number of students of Asian descent, Asian population, and we've put that, looks like I've got it in L4, so I put my data in there. And I could do it with the linear regression, and I did, but I graph it. Look, it's a very, very poor fit. So when you look at the data here, if you look, the basic shape is up and down. Hey, that should suggest, hey, a quadratic model ought to be better. Now, I'm not trying to talk about the shape in between every single point. Sometimes it's up, sometimes it's down, you know. I'm not trying to make that. What I'm just trying to do is kind of get an overall basic shape. And if you kind of look at it, you kind of see, well, looks like there's a pretty definite up and then back down at least. So one change of direction indicates maybe a quadratic model would be better. Here are the models that you can choose from. We've done some of these. We've done linear, we've done natural log, we've done exponential, we've done power function, we've even done logistics. And the rest of these are polynomials with bigger powers. So this was a quadratic, and we'll see later on if it's more or less straight, linear. If it comes up and then turns around once, that way or this way, quadratic. If it looks like you have two changes of direction, up and down and back up again, or down, up, down, like that, cubic. And a quartic used down, up, down, or up, down, or down, up. This would be fourth degree. So these will be, we'll talk about this more next time, next part when we talk about polynomials. So look at the basic shape and decide which one is reasonable. So one of the steps are, if you go back over the steps when I've given you this before, I said, okay, graph it and see what kind of shape is reasonable. Well, a quadratic seems reasonable here. So I'm going to go down here and choose number 5, the quadratic regression. And when I run it, I get the general form, and it gives me A, B, and C. And of course, this is an R square close to 1. The R square was horribly far off of 1 before. Let's see, for the linear, it's only 0.775. Not a good fit at all. But now it's a much better fit here. So here's some more examples, and you can work through some of these examples. So here's something that looks kind of like a, so it looks like this shape. What does that look like? Well, it looks kind of like part of a parabola, you know, if we keep going. So we might use a quadratic model for that. And I did here. Okay, so I'm going to wrap this up now. There are a bunch of practice exercises here, and you should work all these exercises or kind of review over several problems, and then I have some solutions to that at the end. So you can go back and check yourself on those by looking at the solutions. So I'll get this posted, and so there we talk about quadratic relations, and we can see some of their characteristics and some of their applications.